Hello, Dr. Cruz. My name is Matt Fawn, and I'll be doing my presentation on the Capstone project for both the body fat and the heart disease datasets. I'm going to start with the body fat dataset, and I'll be exploring two models, the first being linear regression and the second being logistic regression. So I did go ahead and upload the body fat dataset in here, and it shows just the raw dataset of 252 observations with 15 total variables. So loading the libraries here, I did input readxl and then the R part. So I'll load those. And again, starting with a linear regression model. The first thing I wanted to look at is there any missing data or any NAs that I need to potentially correct for or make adjustments for during the data prep phase. Looking here, you can see no missing data, so that's great news. And so the next one is the summary. And I like to look at the summary of the data set just to see for each of the variables, what is the minimum, what is the maximum. I can see the range in between those. I can also see the quartiles and then the mean. All right, so for model 1, there's 15 total variables, so that's a lot of different things to input to get the body fat. And I know that's the best way to capture someone's body fat, right, is to have all of those measurements. But for the purpose of the project, is there variables that may have a more significant factor than some of the others? So the first thing I wanted to explore is just looking at body fat through the linear model for all the variables. So I did the tilde period of my data set and want to take a look at these. So plotted model 1, and then the summary, looking here at the coefficients, we can see not great results overall. Density is the only variable that is significant at the 0.5 level for p-values. The rest of them are really not significant. So that's not very encouraging to start off with, but looking at the model together, we can see that the adjusted R-square is 98%, which is extremely high. So it is encouraging to see what we can find working through the model itself. I do have a plot command in here. I did plot all the models, but they tended to get worse as I did. So I'm actually not going to be running this command through the presentation for you, just so you're aware of why I'm not going through that. So again, for the results of model 1, we can see that only density, looking through the console window here, is the only significant factor at the 0.5 level. So for model 2, I want to consider what is the effect of the model with just density considered. So running model 2, we can see that it remains significant at the 0.5 level, and just using density alone is 0.9756 for the adjusted R-square, which is still extremely high. But it is a little bit less than using the full model and all the variables. So for model 3, I wanted to see if there is an interaction relationship using an interaction variable with density with maybe one of the other variables, such as age. The p-value for age is not significant. It was 0.192, so not significant at the 0.5 level, but coupled with density, does it become more significant? So that is going to be my model 3, and running that, I can see that density remains significant at the 0.5 level, but density, the interaction variable density and age, does not. It actually gets worse than previous. The adjusted R-square, using it through the model, is exactly it is 0.9756, which is still very, very high. So just kind of, it's interesting exploring this data using the different models to see. So for model 4, I wanted to consider only variables that were not measurements. Measurements such as neck, chest, hip, etc. All those taking those out and just focusing on the X variables that could have an effect on body fat, such as, can we predict it just based on age, weight, and height? Does that give us an accurate picture of body fat? So for model 4, it is just considering age, weight, and height. Through the model, running this, you can see that the adjusted R-square is significantly less, as expected. It is 0.5182, but we can see that what is interesting is that age, weight, and height are all three now significant at the 0.5 level, which I thought was pretty impressive, given what we saw looking at all the variables weighed against each other. The standard error is 7.47, so we can say 7.5 would be our standard error. So any result that we get would be plus or minus 7.5 for that. So for the sakes of running the model and seeing can we get a prediction through here, we're going to use, again, all three of those variables, age, weight, and height, and putting that through R to see what type of prediction we can get. And going to be using this, just first example is off of a 25-year-old, weight 200, and then height 72 inches, so 6 foot. Run that through the model, and we can see we get projected body fat percentage of 18.9%. And then again, that's plus or minus 7 is our error. So not fantastic. Would like it to be much higher, but for the sake of the model, in looking at these different aspects to it, I think it's pretty interesting. So I thought, well, let's run me through it. I'm 43 years old, about 180 pounds and 72 inches, so 6 foot. Running me through there just to see is 17.9%. Again, plus or minus. Hopefully it's a minus, probably a plus. But just that was an interesting way to look. So the next thing I did was plot the variables kind of against each other to see what kind of linear relationships we have between the variables. So the first one I plotted is age and weight. And you can see from the graph itself, if there is a relationship and it's a very weak negative relationship, just based on if I'm drawing a trend line through there mentally. The second plot I have here is age and height. It is, again, a very weak linear relationship, and I would say it also trends negative slightly. Looking at weight and height, plotting both of those is it's a tighter cluster for those results, and I would say it is a positive linear relationship compared to the other two. Wanted to see if quadratic played a factor on the relationship. Overall, it does not, but I wanted to put that through, and this will be our model 5. So I'm going to be using the same three variables, age, weight, and height, but I'm going to be taking the log of height to see what the effect is on it. So I'm running model 5, and we can see the summary here is 0.5011. So again, it performed a little bit worse than, just slightly, than the model 4. And the standard error is much greater with this, right? So it's now plus or minus 25, which is terrible. But the variables are still, they maintain relevant at the 0.5 level. And so we can see if we run the summaries. I just stacked summary 4 and summary from model 4 and a summary of model 5 together to see how they would compare to each other. And then we can run some predictions based on this. So running model 5 off of our 25-year-old male with 200 pounds and 72 inches would be 18.8. And then running, again, model 4 off of that for me comes to be 17.9. So again, not great. Model 4, again, continues to perform the best of these two. We could run dozens of different models to see if we could find other, but for the best, what I saw, the Model 4 performed the best. Now I want to take a look at logistic regression. And so I wanted to use a 70-30 split for the data. So for the training data, I used 176. And then for the testing, we'll put in 76 of those. Running those through R, we can now kind of put the models to test here for prediction 1. We'll be looking for the square root or the RMSE. Again, comparing models 4 and 5 against each other. And then we can see, go back up here to prediction 1, RMSE came to be 5.76, or excuse me, the mean 5.76, and then 5.88. And then looking for k-folds in the data itself to see how does it perform against each other. If we took the different, so taking 4 folds of the total data, how does that perform against each other? And does it give us a better look to see if model 4 or 5 performs better? So running all these through R, we can see down here, as we stack all of those together, I've got them listed out here for each run through the bins, the k-fold. And then the average for model 4 is 5.73, and then the model for model 5 is 5.83. And so again, model 4 appears to be performing slightly better than model 5. And so that's the end of my presentation for body fat. So I'll be sweeping and clearing our data here and uploading our heart disease data set. All right, so we've got in this data set 918 observations, 12 different variables, and we're going to get rid of body fat not to confuse. And again, we're going to load some libraries. I'm going to be loading readxl and then rpart. And again, I'm looking for, is there any missing data, any NAs that I need to account for, potentially. So again, none, which is fantastic. So we will continue. I did run the str function to see the different, between the classification, the numericals, the integers, that are listed on each of the variables, just to see what those are looking like and how the model reads those. So I can see if there's any adjustments that I need to make to clean the data on this part. And then again, I always like to look at the summary of the data so I can see the range, the minimum, maximum, and then the means of those. I did want to make a couple of alterations to some variables here, so because we are getting into a classification problem with the heart disease, because we're really boiling it down to either is yes or no. Does the person have it or not? But I did want to change the variable sex, 0 to 1 to female and male. I think that would help, perform the function a little smoother. So I did run that, and so we'll run our variables here through that. We'll continue to clean. I am going to be changing these to factors, again, to make it easier for the model when we get to the confusion matrix. And then now we can see our 13 variables, how we've cleaned those. Really just male and female is the only one we changed, but we did run the others as factors. And then I only want to keep 8 of the 13 variables, again, looking for those that may play the biggest part in it. When I was preparing for the Capstone project, I actually ran the logistic first so I could see which models are more significant, which variables are more significant at the 05 level for it, and then found these models 2, 3, 5, 6, 9, 10, 11, and 12 were all the ones that I wanted to keep, and of course that includes heart disease. So those will be the ones that we'll be running through the decision tree. And we can look there and confirm now we have 18 observations with 8 variables. We're running 7 X variables, and our Y will be heart disease. And again, just confirming our summary, what that looks like once we've changed the variables, just to help confirm we've done what we want to do in R to help us paint that picture. Now we're going to be, again, doing a 70-30 split for this data set as well. So it'll be the first 643 and then 644 to 918, which will be the remaining 275 remaining. So we'll run our models here. We will view those to confirm we have our variables the way that we want those to look. And then our testing group, we can confirm those as well. We've got all of our entries down here at the bottom. We can see it's 275, and that's accurate the way that we want it. All right, so now we're going to run through the decision tree using our part. All right, so we can see our predictions there, and we can lay those out through the table. So now we get the raw confusion matrix, and we can see 96% predicted correctly of the 275. And we can see all of our different, we'll be getting to those, our accuracy percentage down below. And we can run the library caret to get more in-depth for our confusion matrix. Perfect. And now we have the same confusion matrix that we had on the table, but now we can dive deeper into those and see how accurate our model is. And it came to be 69% accuracy, which is not bad. P-value, we are significant at 0.05 level, which is good. We also have our sensitivity at 65. I am rounding, it's 0.657. 5, and then specificity is 0.7289. So we can see 65.7%, and then for specificity is 72.8% or 0.9%. We can round for those. But pretty interesting results for both of these. I did also plot both of the to see these in more illustrative manner. You can see how the decision tree plots those based on the heart disease data. And I did make that larger, so that way you can see. And did save these to R, making it a lot easier to digest when we're looking at these visually. And then I did also do the explore function, which again puts another illustration on the data and shows it either histogram or bar chart, or kind of the flow chart here for cholesterol based on the results, which gives an interesting view how heart disease, either yes or no, affects each one of these variables and how significant they affect our Y. All right. So now I'll be prepping for our logistic regression, and I will be sweeping and cleaning these out of here, kind of clear that data. And I will be reloading the data set. And now we'll be going through the logistic regression part for our heart disease data set. And I'm going to be running read Excel, caret, rpart, ggplot2, and calplot, just to have those loaded in there for us. And again, through the cleaning of the data, we are still looking into classification problems, so we want to make sure our data reflects accurately. So we're going to be doing the same thing we did for the decision tree, cleaning our data and making sure it looks the way that we want it to. It does. And then again, I'm only be keeping the 8 total variables, 7 X variables, and then the 1 Y will be testing our heart disease. All right, so now these are cleaned the way that we want them. Again, I'm going to be sticking with that 70-30 split for our training data. Will again be the first 643, and then we can confirm that. We have our results here, and then our testing group, and we can confirm those down here. So we have them the way that we want. The data looks the way we want it to, and we're including the variables that we want. All right, so looking through the logistics model, we're going to capture that, and then we'll look at our summary. We can see that all these variables, sex, chest pain, all three types, cholesterol, fasting, exercise, angina, old peak, and then slope, flat and up are all significant. These, the ones for chest pain, down to slope flat, are the most significant at the 0.5 level. And we can see that our standard error is small. We're only within a little over 0.5 percentage plus or minus. So it's very encouraging to see how this would play upon our model for predicting those. If we had, let's say, an example of a patient with sex, chest pain, fasting, exercise, old peak, we input all those and we can have a very strong model looking like that. Do that for logistic regression. All right, so continue to put our responses through here. Looking to do the prediction of the S-curve. We can plot those results, our predictions, and then running our raw table. We can see each patient of the total on the testing group, how those, you can see our ones and zeros indicating they either do or do not have heart disease, and we can see our confusion matrix here, where we correctly predicted 120 of our true positives, and then we can see our accuracy is 0.7855, so 78.5 or 78.6% accuracy, which is pretty good. We have our sensitivity, 0.8219 or 82.2%. Our specificity is 0.7442 or 74.4% there. So exciting project. Thank you for the opportunity to do this, and I hope painted this picture clear for you. It's been a great class, and I appreciate your time. And thanks so much. Have a great day.